Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss mean free path and collision probability. Let's begin. Mean free path. So according to kinetic theory of gases, it was assumed that the molecules, means the gas molecules, are negligible in size. They have no dimensions, but later the scientist Clausius found that these gas molecules have a small but finite size. Due to their finite size, the molecules are constantly moving in all directions with various speeds. So let me take a container where there are the gas molecules. The gas molecules are constantly moving in all directions with various speeds, and they collide with each other. They collide with each molecules and with the wall of that container. They don't exert any force with one another, means that gas molecule does not exert any force with each other during that of collision. Only during that of collision they exerted force, but until there will be no such collision, they don't exert any force between these gas molecules. There will be no such force of attraction or repulsion in between these gas molecules. Between two successive collisions, a molecule moves in straight line. During the successive collisions, the molecules are move like that in straight lines. And the path of a single molecule is a series of these are the some sort of zigzag motion or zigzag path having different lengths, and these paths of different length are called the free paths. So what is free path? The path of a single gas molecule is a series of short zigzag motions. These are the short zigzag motion, such zigzag paths of different lengths are called, and these paths, these are the zigzag paths of different lengths, and these paths of different lengths are called free paths. Are called free paths of the molecules. Known as the free paths of the molecules. And the mean of these paths, if we calculate the mean of these paths, the mean of these paths is called mean free path, is called mean free path. Now, the mean free path is defined as the average distance, means it is defined as the average distance travelled by a molecule between two successive collisions. Is known as that of mean free path. If we take the mathematical way, how the mean free path look like, if we take, if S, that is the distance travelled by a molecule in n collisions, n with the number of collisions, n, that is the number of collisions, therefore mean free path lambda, therefore lambda is equal to S by n, lambda is equal to S by n, where lambda is the mean free path. We have to calculate the expressions for that of mean free path. To derive the expressions for mean free path, we take some assumptions. For the expression of mean free path. The assumptions, first assumptions, all the molecules of a gas, except the molecule under consideration, under consideration are rest, means from that figure these are the consideration molecules. So these considerations molecules are treated as motion, but except to that of consideration molecules, another molecules are treated as rest. This is the assumption number 1. Next assumption number 2. diameter of a molecule is d, let diameter of a molecule is, let d, let diameter of a molecule be d. A collision between two molecules, a collision between two molecules takes place when the distance between the centers, the distance between the centers of two molecules is d. If we take the diameter of a molecule is d, so how the collision takes place means the distance between the centers of the molecules is d. If that is a molecule, its diameter be d, another molecule its diameter be d, then the collision takes place when the distance between the centers of these two molecules is d. That indicates here the collision takes place between these two molecules. In other words, we can say we may describe the collision, we may describe the collision by regarding the moving molecule having a diameter, the moving molecule having the diameter 2d and the other molecules as point particles. Point particles means there will be the container where the gas molecules are motion randomly with various velocities in various directions. If we take a small segment of that of container, if you take the cylindrical segment, this is the cylindrical segment, having the diameter, its diameter be 2d. The collision regarding the moving molecule having the diameter 2d and the other molecules as the point particles, and the length of that cylinder as c. Right here, let a single molecule, let we take this is the first one, but here we take, let the single molecule, let a single molecule of equivalent diameter to d is moving through a gas of point molecules, moving through a gas of point molecules. Let the velocity of the molecule be c. Let the velocity of the molecules that pass through that of diameter of 2d, the velocity, let the velocity of the molecules is equal to c. This molecule will collide with all other molecules in 1 second, whose centers lie within that of cylinder of radius d. Did you take the cylinder of radius d and the length c? So here what exactly that figure indicates, the molecule which are under the collision category, the molecule will collide with all the molecules in 1 second. Whose center lie within the cylinder of radius small d and length small c. These gas molecules are under the category of collision. Therefore, we take the volume of the cylinder, the volume of the cylinder, V is equal to pi d square c, c with the length, so pi d square c is the volume of that cylinder. Let the number of molecules per unit volume of the gas, let the number of molecules per unit volume of the gas be small n. Small n is the number of molecules per unit volume of that of gas. How much number of molecules are within that of unit volume? Therefore, we know the number of collisions per second, is equal to number of molecules in the cylinder, that is the number of molecules in the cylinder. Here number of collisions is same as number of molecules in that of cylinder. That is capital N and the number of molecules in that of cylinder is the volume of the cylinder, into small n, small n the number of molecules per unit volume in that of gas, that is the total number of molecules in that of cylinder, which is equal to the number of collisions per second. The volume of the cylinder, that is pi d square c into n here, that is n number of molecules in that of cylinder. Now the distance travelled by the molecule in 1 second is c. Distance travelled by the molecule in 1 second is equal to small c. Therefore, mean free path is equal to distance travelled in 1 second, distance travelled in 1 second divided by numbers of collisions per second, numbers of collisions per second, that is mean free path lambda is equal to distance travelled in 1 second small c, number of collisions per second, that is pi d square cn, number of collisions per second pi d square c into n. 1 c cancel out, so lambda is equal to 1 divided by pi d square cn. Where pi d square is equal to sigma, which is known as the collision cross section, which is known as the collision cross section. To derive that equation, all the molecules except one have been considered to be at rest, as you take the assumption, means the molecules which are considered are under motion, and except the molecules which are not considered are treated as rest. By taking this assumption, we take the derivation of mean free path. Now, two scientists, one is Clausius, another one Maxwell, who again proposed the mathematical expression for mean free path according to their own assumptions. So, first scientist Clausius assuming that all the molecules are moving in all possible directions. Clausius assumption that all the molecules are moving in all the possible directions with a constant speed. According to this assumption by Clausius, he derived the expression for mean free path. So, the mean free path expression lambda will be 3 divided by 4 pi d square n. Again, another scientist Maxwell his assumption to derive mean free path was, he considered the distribution of considering the distribution of molecular speed and he derived the expression for mean free path. Therefore, mean free path lambda is equal to 1 divided by root 2 pi d square n. This is the mathematical expression proposed by Maxwell, root 2 pi d square n. Means mean free path lambda is inversely proportional to the number of molecules per unit volume. Look at these three expressions. This is the expressions as we take the considering molecules are in motion and other molecules are at rest. This is by taking the assumptions by Clausius. This is the assumptions made by Maxwell and his mathematical relation to that of mean free path. From these three expressions, it is clear that mean free path from these expressions, it is clear that mean free path lambda is inversely proportional to the number of molecules per unit volume small n. Mean free path lambda is inversely proportional to the number of molecules per unit volume, that is the small n. Now, we can express the mean free path in terms of pressure and temperature. Expression of mean free path in terms of pressure and temperature. Expression of mean free path in terms of pressure and temperature. How we express that one? We know that the gas equation for 1 mole of gas equation for 1 mole of gas, an ideal gas, that is PV equal to RT. Since R is equal to NK, since R is equal to NK, N be the Avogadro's number and K be the Boltzmann constant. N is the Avogadro's number, K be the Boltzmann constant. So what we have? PV is equal to NKT, or P is equal to N by V KT. N by V, which is known as small n KT. Small n, where small n is the capital N by V, that is the number of molecules per unit volume. Now N is equal to P by KT. Now putting the value in the expression of mean free path. Therefore, mean free path mean free path lambda is equal to kt divided by root 2 pi p d square. Means in place of n we substitute p by kt. So lambda will be kt divided by root 2 pi p d square. From this expression, therefore first lambda is inversely proportional to that of pressure, and lambda is directly proportional to that of temperature. In this way, the mean free path depend upon pressure and temperature. Next, we have to discuss how the collision probability exactly looks like. We have to define the collision probability. Collision probability. Although a molecule suffers collisions quite irregularly, but still there will be a certain average rate of collisions if considered over a long period of time. The average rate of that of collision, suffered by a molecule per second is called collision rate. The average rate of collision suffered by molecule per second is called collision rate, and it is denoted by P with the collision rate. Therefore, the number of collisions suffered by the molecules in time t. How much number of collisions are suffered in time t, which is known as p into t, that is a collision rate into time. If the mean velocity of the molecule be small v, if mean velocity of molecule is equal to small v, then the total distance travelled by the molecule in time t, then the total distance travelled by the molecule in time t is equal to v into t. Is the total distance travelled by the molecule. V with the mean velocity, this is the total distance travelled by the molecule at time t. Then the average distance travelled by the molecule between the two successive collision is known as the mean free path. Therefore, mean free path lambda is equal to total distance travelled in time t, total distance travelled in time t divided by number of collisions suffered in this time. Number of collisions suffered in this time. Therefore, lambda will be total distance traveled in time t, that is v into t, number of collisions suffered in this time, that is p into t, t cancel out, so lambda is equal to v by p. Now if we consider those mean free paths is only where the molecules possess the velocity small v, and at that time the mean free path is considered as lambda of v. So let we take, if to relate that particular expression, if we consider those mean free paths only where the molecule possesses velocity small v and denote the mean free path, that is lambda of v, mean free path lambda of v, and collision rate only for those molecule of velocity v by p lambda. Mean free path is denoted by lambda of v and the collision rate is denoted by p of v, corresponding to that of molecules having the velocity small v. Therefore we write lambda of v is equal to v divided by p of lambda. Since p into t, pv into t, that is the what we take, that is the number of collisions suffered in time t as pt. So here pvt is the probability, that is the probability that the molecule of velocity v, suffers collision in time t. Pv into t is called the probability, and the term p of v we may call the quantity p of v as collision probability. P into t is known as the probability and p of v, that quantity, is known as the collision probability. This is for collision probability. Now with the help of this visual exercise we understand what is mean free path, its mathematical expression, and the assumptions to express mean free path. These are the two assumptions. By using these two assumptions we derive the expression for mean free path. This is the derivation of that expression of mean free path. This is the mathematical expression of mean free path. According to Clausius, taking this assumption, he derived mathematical expression for mean free path, and Maxwell, taking that assumption, derived the mathematical expression for mean free path. From all these expressions, we conclude that mean free path is inversely proportional to the number of molecules per unit volume. And then mean free path in terms of pressure and temperature. This is the mathematical expression, how mean free path relate with pressure and how it will be related to temperature. And last, about collision probability. What is collision probability? What is probability? What is collision probability? So, with this useful and informative notes, let me wind up this session. Thank you.